Oh,
What was the question?
when do I want the unknown lab? The unknown lab. Let's see. Probably not this week. Next week, since there still might be people finishing it up this week, so we'll have it due next week on Thursday. The unknown lab is going to have two parts again. So just on one page, you're just going to, report the cations found. For example, iron 3, etc. Just list them. Cations found. So this would be like part 1 of the report. We could have it all part 1. Or we could have the points spread out over part 2. One. For part 2, you would just go through all the known observations and equations, and you would list them. So there would be 10 of these, starting with silver, to, what was after silver? Magnesium?
Silver is the last one or after silver?
After silver.
Is iron.
Iron.
That's essentially all the equations you went over.
Yeah. 10 total. So it wouldn't be just for the cations that you found, but it would be for every single ion. This could be written, handwritten is fine. You don't have to type it.
No formal.
But can we type it?
You can type it if you want. Yeah. Some people type it. I've received lots of.
Observations is next stage equation of what?
The observation is a very simple observation. Unknown AQ plus AG. Well, not unknown AQ plus HCl yields. YPPT. Just. All you have to do is copy the stuff that I wrote on the board, and that's part 2. No formal report for this. The formal report, there's so many reactions that are occurring here. In the formal report, this would be quite a lot of work, because you'd have to go into detail explaining each of the reactions. This is what's happening in this particular reaction. The reagents. Why was this reagent chosen instead of that reagent? It depends on how much detail you want to get into things. For example, here when you're talking about the silver analysis in a formal report, somebody might ask, why HCl? What other acids could you have used? What other acids could you have used? You could have used sodium chloride. You didn't have to use hydrochloric acid. Sodium chloride would have worked. What else would have worked? Would hydrobromic acid work? Hydrobromic acid would have worked. What else would have worked? Hydroiodic acid. Certain things would have worked. And so, like in a formal report, you dig into the topic in a lot more detail, because you have to anticipate. You have to anticipate these sorts of questions, and you want to make sure that you answer these things, because somebody is going to legitimately ask, why are you adding HCl? Why don't you add sodium chloride? Why not hydrobromic acid? And so in a formal report, in the discussion section, you can talk about those types of things if you want, It's not absolutely necessary. You could say, we use HCl because somebody told us, the procedure told us to use HCl, right? But as you progress in science, science, you have a lot of curious people, and those curious people ask a lot of questions, and they're going to start asking you about things, And so when you write a report or do something like this, you're always thinking about those things. You know, why am I doing this way? You know, are there any alternative ways of doing this? You know, and how do I know? You know, this is a big question. How do you know you got what you got? You know, what convinces you that you have what you have, and how can you convince other people that you have what you have? And so this is the discussion. The discussion is not merely I mix this with that, I got a white PPT. You know, the discussion is much more. This is why I was reading through some of the, and I want to get those back to you today. Let's see. I'm reading through a lot of the rough drafts, and I noticed, you know, yeah, some people are going into it in a lot of detail. You know, other people are just saying, well, I got 80% yield, and that was about it. You know, but you need to go into some detail into the chemistry of what's happening. And the chemistry of what's happening is, you know, what are you doing first? I don't want it all combined. You know, if you just copy the equation out of the book, which you think is probably pretty good, well, that's not what I want. You know, I want you to dig into the reactions a little bit more. You know, with what's happening as far as the chemistry. And people have been digging. You know, if you just repeat what I said about it, that's good. You know, but you can also add more to what I said. You know, there are a lot of places where you can make it a much better discussion section. You know, doing a little bit of side research. That will help. And so let's talk about, you know, how I would have you know, maybe approached the silver analysis. You know, this you don't have to do a formal report, but we can talk about, you know, if we were doing silver, you know, analysis, in a formal report, what would you say about it? You know, would you say I took 10 drops of unknown or 20 drops of unknown? You know, even like 10 or 20 drops of unknown, somebody might ask you, why are you using that? Why don't you use more? You know, why don't you use less? Use less, then you don't need as big. You know, a lot of people want to do micro analysis, you know, with minimal sample size. Sometimes it's hard to come by the unknown. Right? But somebody might ask you, why are you using 10 or 20 drops or 30 drops or 40 drops? You know, is there some kind of reasoning to that? Does anybody remember why we were talking about the amounts? Huh? Well, with one, you want to use more. The more you use, the better, right? The more you use, the more precipitate you generate, and the easier it is to see things and separate, right? The less you use, by the time you're at the 20th, 30th step, you might be down to trace amounts of precipitate. You could barely see it, right? Because in each separation, you lose a little bit. And so, what did we talk about? Why don't you just use a whole bunch? Well, I told you one thing. I told you not. Well, I might have told, might have or might not have told you to not dilute it. You know. For example, what is the whole reasoning behind diluting it? This is a question I'd like to ask the author of that experiment. Why the heck are you diluting it? It doesn't make any sense, or does it? You know, what's the argument for diluting it? Okay, that's fine. You know, we could take that. That could be perfect in your discussion section. We dilute it with 10 drops of water so that it makes the precipitate maybe stand out more. So it isn't just down there at the bottom curve of the test tube where, you know, the light is kind of diffracted in weird ways. Maybe that's it, to bring it up into the nice parallel cylindrical part of the test tube. Is that it? Could be, but you know, we're centrifuging these things anyway. So, so basically, a discussion section is this. You know, when you write a formal report like this, you send it out. In science, you have to send it out to what they call referees, and the referees, what they do is they read it and then try to help improve the paper, right? And so you try to anticipate, you know, the typical questions that a referee would ask, you know, things about your analysis, and you try to address those in your paper. Some things you don't have to address because they're simple. You know, why do you use a 250 milliliter rather than a 500 milliliter beaker? You know, that's should be self-explanatory. But certain things like, why do you dilute it? You know, why did you use HCl? Why not sodium chloride? Well, there might not be any reason. You know, well, you know, a good thing would be. So in a discussion, you'd say, well, we used HCl, you know, rather than sodium chloride too, or some other precipitating agent too, and that would require a little bit of research, maybe, right? Or you don't have to include that, but do you see there are a whole bunch of points in this lab, in lots of labs, where you can add much more to the discussion section, you know, to make a much stronger paper. Because if somebody's reading a paper and they read one where I just mix this with this, you know, or versus somebody who said, well, we chose HCl because maybe it keeps the pH down, so you don't run into hydroxide precipitates or something like that, you know. There's certain reasons for, and it's not that you have to know every single step of the way, but you know, if you see something that you go, I wonder why I'm doing that, then maybe you might want to research that and add that to the discussion section.
It wouldn't be good to use sodium chloride though, because then you might be introducing sodium ions.
Right, yeah, exactly. You wouldn't want to use sodium chloride because sodium ions are a potential unknown, and that would be a really unfortunate thing to do. But it happens, you know, people are doing iron analysis and they're adding iron to it. Yeah, they're going to test positive. It's happened many times where they get mixed up. And so, yeah, little things, you know. Maybe that's too obvious, you know, something like sodium chloride, so you don't necessarily have to include that in, but like hydrobromic acid, why not precipitate out the bromide instead of the chloride, you know? So that's just one step, you know, there are many steps here. But you don't have to do it for every single step. If you see something where you can add a little bit more depth to it, that's kind of good. How many, you know, a lot of people will combine all three. It's like this, you know, aqua regia. So gold will dissolve in aqua regia, solid gold. You know, and so a lot of people just write out the balanced chemical equation. But you know, in a discussion section, I just don't want the balanced chemical equation written out. I want you to tell me, you know, why HCl, why nitric, why this combination of HCl and nitric? What is the HCl doing that the nitric acid can't do? You know, are they the same? And so here, you know, in a discussion section, you can start talking about things like oxidizing acids and non-oxidizing acids. Non-oxidizing acids are just called mineral acids. Mineral acids, well, all acids are oxidizers, right? All acids are oxidizers because all acids contain, all Bronsted acids contain H+. And so, let me open the door here for you. So if you combine it all together, then it's not really illustrating the reason why we're adding these. You would talk about this separately, so you break up this. You know, obviously these reactions just happen at once, right? But what we want to do is we want to separate it and break it into parts. Just like your synthesis, you don't want just one, well, this is the overall reaction. But you want to break it up into parts because these two acids do different things. In fact, one is acting as an acid, the other is not. You know, and even they really aren't acting as an acid because is gold a base? You know, not really. And so these acids are acting in different ways. Well, that's okay because acid-base is just one of the properties that they can have. What are some of the other properties? Metathesis and redox. And this is Bronsted. There's also Lewis acid-base reactivity. And so, you know, you go into depth. You know, nitric acid is what we call an oxidizing acid because it's a powerful oxidizer compared to HCl. HCl is a moderate oxidizer just because of the H+. But we have nitrate here. It's going to be a powerful oxidizer. In fact, I just was sent an email out. Did I tell you about the explosion I had in the waste in hood number, that hood right there? Did I tell you about that? I had two waste jugs because this person was making up a lab. It was a synthesis lab. It was a different synthesis, but they had the same thing. They had to wash with ethanol, right? And so they missed the lab. So I said, "Okay, you can go ahead and make it up during this lab." But during this lab, I had them do the anions. When you do the anions, like detection of nitrate, you have to add concentrated sulfuric acid. So you have a very acidic solution with nitrate in it, which is going to be a powerful oxidizer. So I told the person, yeah, don't just keep the waste separate. You know, we have the old waste and then this lab's waste. And so we had a jug full of nitric acid with concentrated sulfuric acid in there. Sulfuric acid is also an oxidizer. And so just powerful oxidizers because they're doing the nitrate, the brown ring, they call it. Which we didn't do this semester, but it's all right. So the person poured the ethanol rinses into the nitric acid waste. Boom! The waste jug, you know, exploded. But fortunately, it didn't explode. Just a big fireball happened. But so I get a memo in Texas from so I was sent out this from the dean of the chemistry department saying, let's not have this accident happen here, but it was too late. 5-6 years too late. Something like that. But they had a nasty explosion in which the waste jug actually did explode. 4 or 5 people were sprayed with waste in the fire. But fortunately, nobody was seriously injured, I think, because it probably was in the hood. But anyway, fortunately, we're really lucky. I was really lucky because the person was kind of reaching to get to the top, so the hood was up and their head was inside the hood, and then they were pouring this, and their face was totally red, and then their hair got burnt here, but it was okay. No glass shooting out. But after that, then no more synthesis makeup. That was the last time I did synthesis makeup during qual, this lab, you know. I learned my lesson from that. Also, you know, I figured repeated, you know, because I mentioned the waste thing about 3 times because, you know, powerful oxidizer, powerful reducer, but it just didn't register. And so after that, then I decided I need to talk more about redox chemistry. Otherwise, people don't have a feel of what maybe still people don't have a feel for redox. But anyway, you need a powerful oxidizer to oxidize gold. And so that's what the nitric acid is doing. It's oxidizing the gold 3, but gold 3 is so unstable. Gold 3 will easily oxidize water. Water is pretty steady. And so, the HCl is there not as an acid, but HCl is there as a base. And so the HCl attacks the gold 3 as a Lewis acid-base reaction. And so you would explain this, in a discussion section, talking about this, nitric acid, stuff like that. So are there any questions about you don't have to do this for this report, fortunately, but if this were turned into a formal report, it would be very long, like a 50-page report or something, right? Going in depth and into all those reactions. Yeah. Well, how many reactions do you guys have in the synthesis lab? 4, 3? Okay, yeah. I noticed a lot of people also didn't talk. When you do synthesis, another thing that's very important is, it's not just the synthesis, but it's also what? Remember what I told you about the crystals? I told you don't worry about the yield, worry about the purity. Another thing that we want to do in synthesis is we want to synthesize the highest purity possible. And I noticed very few people talked about it. Purity. Maybe you're going to get to it, because I also saw a lot of people didn't get very far just yet, but maybe you'll get to it. But you need to talk about that as well.
So, like, when we're measuring purity, we just look at it and then oh, it's pure.
Fine, you could write that in your discussion. I looked at it. From my judgment, it looks pretty darn pure. Yeah. There's certain things that are going to obviously be indicators of impure stuff. Like, for example, if you don't have crystals and it looks like a sludge, just some kind of oil deposit on the bottom, maybe there's some kind of contamination there, or discoloration, or those. So actually looking at it is very important. You want to look at it. Some people take pictures of the crystals and include it in their report, to show. Also, the crystals have a lot to do with it, because when you're trying to make ultra pure stuff, you try to make a single crystal. The bigger the crystal grows, that means that there's got to be fewer impurities, because one impurity here leads to defects, and that would distort the structure, which means you wouldn't get a nice big single crystal of it necessarily. And so nice big crystals are always good for purity, that type of stuff. But we talked about it too. We talked that's not entirely satisfactory, right? How do you know? How can you prove to somebody it's pure? If somebody asks you, how pure is this stuff? How could you prove it to them? It's important. Usually, synthesis people, what they do is they don't necessarily take people's words. There have been stories where you grab a bottle off the shelf, right, and you start your synthesis, or you buy a brand new. Let's say you buy a brand new bottle of reagent, starting reagent. And so you're thinking it's brand new. You have they have the analysis sheet, talking about how pure it is and the contaminants in there. There have been cases where people have bought fresh reagents and somehow it got contaminated, for some reason. And so what they thought they were starting with wasn't. And so in every synthesis lab, what people do is they first test their reagents. They test the purity of their reagents. This is very common. And so if you do a little bit of research, you can find out how do people test the purity of their reagents. And then add that to the paper. Did we test the purity of the reagents? No. No, we didn't. So, it's not always done, but for stuff, certain things. There's a very famous story at from the Lincoln Laboratory at MIT. There's a group of physicists there that were making this material that had very interesting electronic properties. And so it was a very simple synthesis. They just took this powder and mixed it with this powder and heated it up in the oven. And then they got their stuff that they were after. But it wasn't until about 5 years later that they found out what they thought they had wasn't what they had. So lots of people tried to repeat what they did but couldn't. And so they went back and they tried to figure out why they couldn't. And the reason why is because their starting reagent, which they thought was high purity, I think it was titanium something, turned out not to be. It was something else. And so they were introducing a whole bunch of contaminants. And so that was about 5 years worth of work that was, in a way it was wasted, in a way it wasn't, because they still developed, just they had to redo all the analysis on it, and once they had the correct composition. And so the thing in like in Chem 4 and in general chemistry, you're protected, right? You have this procedure, you do this procedure, and that's it. And what you see is what you should get, right? But when you start doing science, like because science, you don't want to just be repeating these types of things. You want to be doing new stuff as well. When you start doing new stuff, you aren't protected. You have to defend yourself, whatever you're synthesizing or whatever your analysis, it has to be well argued. You have to have solid justifications for everything that you think, and so that's one of the big things that I learned from going, because when you start off in science, there's always the professor you could ask for the answer, or you can always look up the answer. But when you start getting a little bit farther, and it's not that much farther, you start getting a little bit farther, there's nobody to ask, and then you have to justify everything on your own, or you have to figure out the right answer as best as you can on your own. And so this is a start. This paper is good because there are definitely some weak points, right, in this lab. And you can talk about the weak points in this lab and how to make it a better synthesis or better experiment as well. All right. So that's the lab for. Well, I talked about two labs. This is simple. This you don't have to think. Just copy, write it down, and in that process, hopefully, some of these reactions register. And then the formal report, which is a synthesis. We get caught up in taking certain things as like givens, like postulates, like. And this is, I sometimes I ask this question. I normally ask this question in Chem 1A, right? Chem 1A people know this. Do atoms exist? What would you say? Do atoms exist? Sure, they exist, because people start learning about atoms in probably elementary school now, or at least junior high school, right? And so you've been told that atoms exist, so everybody takes it for granted. But then when somebody asks you, what kind of proof do you have that atoms exist? Then it's surprising how many people cannot come up with proof that atoms do exist. Do you have proof that atoms exist? enough proof that you can at least convince somebody who doesn't believe in atoms that atoms do exist? I had somebody who didn't believe in atoms come to my office and give me his book, his self-published book. It was about this thick, talking about, he came up with a whole bunch of new names for different things, and I still have the book if anybody's interested in it. But he had all these arguments that atoms don't exist. So what am I going to say to him?
But were they good arguments?
I haven't read to be honest, I haven't read very far. I read the first couple of pages, and that's about as far as I got because they weren't very good arguments. But we have very good arguments that atoms exist. And so you got to start thinking in that way. And so this is why I guess all that critical thinking is so important in science, because scientists are very critical people in general. And they don't. I guess a lot of them. In science, it's not trying to attack you, but trying just to help strengthen your work. And so, like for example, when I send out a paper, you get pages sometimes of comments. So, what are you doing here? What's going on with this? Are you sure about that? What makes you think this? Those types of things. Just very curious. And then if you can't come up with decent arguments for that, then they aren't going to publish the paper. Well, anyway, let's talk. I need to do a little bit of catch up here as well, because I want to finish up chapter 17 so we can have the test on chapter 17 next week. I was thinking next week on Tuesday. What do you think? Thursday? What lab do we have scheduled next week on Thursday? pH titration. pH titration day 2. Day 2. pH titration. All right, maybe if we do it on Thursday, then you have to prepare the pH titration for Tuesday. You're gonna have to complete it on Tuesday, or at least you get one good trial of it on Tuesday. Oh, speaking about pH titrations, let me talk about one more type of problem that is typical in a pH titration. And so let's have 10.0 milliliters of this case. I'm going to go with 0.200 molar HCl, and then I'm going to titrate this with 0.100 molar of sodium hydroxide. And so how many milliliters of sodium hydroxide, HAC, sorry, HAC. How many milliliters of sodium hydroxide will it take to hit the equivalence point here? So the shape of this is it's monoprotic. It's a weak acid, so the weak acids start off at a little higher pH. Here. And then within about 2 to 4 drops, it just skyrockets. This happens like probably within 4 drops, the pH climbs up about 4 to 6 pH units. Boom. There's a dramatic change in pH near what we call the equivalence point. 2 drops before the equivalence point, the pH is down about 2 pH units. 2 drops after, it's about 2 pH units. But the equivalence point should happen where? Roughly. 10 milliliters? This one is a trick question. 20 milliliters. This is the acetic acid is twice as concentrated. So this should be 20 milliliters here. Now, the equivalence point, the pH is going to be around the 8 to 9. pH is going to be a little high. 8 to 9. We can calculate it. It's just the sodium acetate solution here. The equivalence point. Now, that's different than the end point. What is the end point? The end point is where the indicator changes color. And so if we use phenolphthalein for this particular titration, do you know where phenolphthalein starts to turn red? Does phenolphthalein start to turn red at pH 7? No, actually phenolphthalein starts to turn red at around pH 9 and then just stays red. Here. Phenolphthalein stays red. And so phenolphthalein seems to be the perfect indicator for this titration because, the end point and the equivalence point are about the same, around pH 9, let's say. Does it seem like the perfect indicator? Otherwise, we'd have to stick a pH meter in here and then take a look at it. And then it's going to just stay red, as we go past it. But what if we were titrating sodium hydroxide with HCl? If we titrated sodium hydroxide with HCl, then the equivalence point will be the salt sodium chloride. Sodium chloride is a neutral salt. And so if we were titrating HCl with sodium hydroxide, the equivalence point would be at pH 7. If it's pH 7, well, phenolphthalein doesn't turn red until about pH 9, light pink. Would phenolphthalein work in that case or not? It would definitely be an error because if we titrated to pH 9 when we should have stopped at pH 7, we've gone too far. We overshot the equivalence point, right? But how much did we overshoot it by? And so the answer is, when you look at how steep this rise is here, it's less than a drop. In other words, to go from pH 7 to pH 9 is probably less than a drop in an HCl sodium hydroxide titration. And so because of how vertical this is, we're okay. In fact, we could use indicators that change color, and there are other indicators that do change color even before 7. There are indicators that change color like at 5. With a pH 5 indicator, that is, it's one color up to pH 5 and then it switches to another color after pH 5. That means we'd stop here. Would a pH 5 indicator work for this titration? No, it would be off, but how much error does that introduce? Negligible error, because it's so steep, this vertical rise, that it's probably going to be less than a drop. And less than a drop error is acceptable. Especially considering the fact that you usually do a standardization process in which that error turns into systematic error, which cancels itself out. Because you're always overshooting or always undershooting, which leads to a systematic error. And so that's okay. As long as we have an indicator that changes color on the steep portion, then we're good. But if the indicator changes color down here, are we anywhere close to the... No, we're way off. And so we got to just make sure with with an indicator, it changes color in this range. Now with phenolphthalein, let's take a look at phenolphthalein in general. What phenolphthalein is, it's an organic acid. And we just call it HIN. IN for the indicator anion. And so HIN, this is what we call the acid color. Here. And then we know H2O, this is going to yield hydronium plus IN minus. This is the base color. And we can switch easily from acid color to base color and back and forth like a seesaw by using Le Chatelier's principle. We use Le Chatelier's principle. In other words, this. How can we do this? All we do is we adjust the pH. If the solution is very acidic, it has lots of hydronium, which shifts the equilibrium to the left, meaning it's going to be the acid color. Phenolphthalein, the acid color is colorless, right? If we decrease the pH, that's making it more acidic. If we increase the pH, makes it less acidic. That means the hydronium goes down. So increasing pH is going to shift this to the right and make more base color. And so when does one color dominate and the other color not dominate? And so, for example, if it were tilted like this, favoring the acid, then it's mostly acid. This is a seesaw, let's say. Or mostly base. Or kind of in the middle. And so what we have here is this. Now, this type of equilibrium we can describe in terms of this. If we have significant amounts of both, then it's a weak acid and its conjugate base, and the pH dependence can be looked at in terms of the base to acid ratio. So, let me erase this here. So, what we say is this. If the base to acid ratio is greater than 10 to 1, then the solution has the base color. In other words, the base color dominates. I need to make room in the middle here, but if the base to acid ratio is 1 to 10 or less, then the acid color dominates. And if it's between these two, that is, the ratio, let's say, is greater than 10 to 1, but less than 1 to 10, then we have an intermediate color. And so, in other words, it's a mix with two colors. So, for phenolphthalein, the acid color is colorless, and so as long as we have 10 parts more acid than base, then we should get colorless.
Shouldn't it be the greater than 10 to 1 for both of them? Should be greater than 1 to 10 or less than 10 to 1 in the middle? Because it's between the two.
Okay, thanks. Yeah, it should be greater than. It should be bordered by these two. Yeah, thanks. Like 9 to 1, 1 to 1. 1 to 1 should be an intermediate color. one part of base, one part of acid. And so for phenolphthalein, the acid color is colorless, the base color is red, and so colorless and red make light pink. And so what we see is this then, that the base color is going to dominate when the pH is greater than the pKa plus 1. The acid color dominates when the pH is less than the pKa minus 1. And then the intermediate color is going to happen when the pH is equal to the pKa plus or minus 1. And so what is the Ka for phenolphthalein? Well, the Ka for phenolphthalein, or the pKa, well, let me just write the pKa. pKa is about 9 for phenolphthalein. All right, so we're doing some Le Chatelier's shifting back and forth, not necessarily for indicators. Maybe we're doing an indicator. Shifted back and forth, but mostly for other reactions. All right, so there are many indicators. Look in the book. I was going to show the slide for. And they're all based on, their pKa. They're going to have different pKa. So you usually use an indicator with a pKa close to where you want it to change. All right, one more calculation I wanted to do. That is, when you overshoot with phenolphthalein, really what you want is this. You want to go from colorless to colored within a half a drop, right? In a normal titration. But if you overshoot, like a lot of people say, is this too dark of a red? Actually, I have no idea, because once you overshoot, it just looks red. And you could overshoot it by milliliters and milliliters and milliliters, and it still looks red. And so sometimes it's difficult to tell, how much that's overshot by. That's in a normal titration, but next week we're not doing a normal titration. You're going to be adding phenolphthalein, but we don't stop. This is why sometimes I think we need more time, because, I don't know, people are so used to stopping. You want to get it just right, half a drop or something, colorless to colored. They stop, clean up, wrap everything up, and then they go to plot their titration graph, and I see this for the titration graph. Looks good, looking good, and then it stops here. And I ask, what happened? Where's the rest of it? No, they hit the end point here of the titration, so they stop. We aren't stopping. We're going to keep going, because we want to see the rise in this, and then we want to see where it flattens out. When we're in the excess base part, then we're going to keep going until the pH gets to, up to where? What are the pHs typical around here? This is just excess sodium hydroxide. We'd expect pHs, 12 to 13 maybe. We aren't going to get to 13, actually. More like pH maybe 11 to 12, right? And so let's see, how many milliliters would it take to get to pH 11? At pH 11, the milliliters of sodium hydroxide would be what? Because we don't want to stop at that. We want to keep going so that we see the whole structure of this titration curve, where it rises and then it goes out. And so let's use the previous setup where we have the 0.200. So what did I say? 10.0 mils of 0.200 molar acetic acid with 0.100 molar sodium hydroxide. Now pH 11, is this going to be in the buffer region here? Is pH 11 in the buffer region? No, is pH 11 at the equivalence point? No, pH 11 is beyond the equivalence point here. And so how would I figure out how many mils it will take to get to pH 11? The ice table, exactly. We need to set up the ice table. So let's go ahead and set up the ice table. But before we do the ice table, what do we have to do?
Solution.
We have to do step A, solution dilution. And so step A is we're mixing the sodium hydroxide solution with the acetic acid solution. How much acetic acid do we have? 10.0 mils. How much sodium hydroxide do we have? How many mils of sodium hydroxide are we adding? We don't know yet, so what should I call it? X. Or should we use X? Yeah, okay, let's use X mils. Right? So we got X mils. All right, now what do? We do the same process, right? Which is, now we're going to have a total volume of 10.0 plus X milliliters. And then we have to figure out the new concentrations, right? So what are the new concentrations? The sodium hydroxide concentration is going to be X over 10.0 plus X times 0.100 molar. And then the acetic acid concentration is going to be 10.0 over 10.0 plus X times 0.200 molar. Right? All right, so this is what we call the initial sodium hydroxide. This is the initial acetic acid. All right, after we're done with step A, then we do strongest base of the strongest acid. Step 1. Acetic acid plus sodium hydroxide yields sodium acetate plus water. And so what is the initial concentration of acetic acid? Well, maybe I'll use this so I don't have to write this whole thing out. I'll just call it HAC initial. The initial concentration of sodium hydroxide would be NaOH initial. Now the change here, this is going to be 0, right? What's the change going to be? Now, since I already used X, let's use a different variable. What should we use? Y? Okay, let's go ahead and use Y. Or, so we'll just say minus Y molar. Actually, you know what? Don't I already know what Y is? Yeah, because K for this is very, very large. And so what is the limiting reagent here? I know where I am in the titration. It's got to be HAC. And so minus HAC initial plus HAC initial, the concentration, whatever it is. And so at the end of this, I'm going to have 0, right? Molar. And then I'm going to have NaOH initial minus HAC initial, and then HAC initial. All right, what's the next step here? NaOH plus NaC. Both of them are bases.
The strongest hydroxide.
So we looked at, here, we go, both of these are bases. The strongest acid now is going to be water. And so it's just Kb. And so all we're looking for are hydroxide contributors to water. And so we have NaOH is a hydroxide contributor. NaC is a hydroxide contributor, and water is a hydroxide contributor. And so at this point we ask ourselves, should I worry about the NaAC contributing? Should I go and set up one more ice and have NaAC contribute? Yes or no? No. NaAC is pretty weak base, so it doesn't really contribute much. Yesterday, what was I doing? Phosphate? So if I have a mixture of sodium hydroxide and phosphate, I forgot to mention this. Probably because I didn't talk about phosphate that much to you guys. But phosphate is a little bit different than your typical weak base. One, it's tribasic, it can accept 3 protons. And 2, its Kb is pretty big for a weak base. If you look at the acid and base chart, at the border between the strong acids and the weak acids is hydroxide and hydroxides on the strong acid side. On the weak acid, strong base side. Hydroxides on the strong base side. On the weak base side, right at the borderline is phosphate. And so, since it has a fairly big Kb, phosphate could be a significant contributor. It's like sulfuric acid. Ka2 for sulfuric acid is fairly big, so Ka2 is a significant contributor to the hydronium. Well, phosphate, the Kb1 is fairly big. And so but for acetate, it's pretty small. We did this calculation, didn't we? Did we? And we saw that the additional hydroxide from acetate was pretty much negligible. It really didn't change the pH much, correct? All right, so this is what we're going to do. We know the pH. pH is 10.00, which means the pOH must be 4.00, which means that the hydroxide ion concentration is 1.0 times 10 to the minus 4 at equilibrium. And so if this is the hydroxide ion concentration, and all the hydroxides coming from the sodium hydroxide with negligible amounts from acetate and negligible amounts from water, then we can just say that this has to equal this, right? And then solve for x. Solve for x.
You said we were doing 11, not 10, for the pH. So the pH should be 10.
Oh, shoot. This is 11, so this will be 3. This will be 10 to the negative third. You're right. Does that make sense? So, could you do a diprotic acid? Could you do the same type of calculation on a diprotic acid? What would you do on a diprotic acid? Would you stop after step 1? No, you'd have to do step 2. After step 2, then we have the same situation. You know, base contributors. Kw, hydroxide. Kb. And so for diprotic acid, it's just one more step here. And so you just introduce, rather than this, we'd introduce one more in here. And then whatever the limiting reagent is, which would be, in this case, if it were diprotic, would be that. For triprotic, it'd just be 3 steps. And then figure it out at the end. Does that make sense? And so the monoprotic is the easiest. Diprotic is just one step harder, but it's not that bad. You can try it. Well, we aren't going to try it. So those are your standard calculations for pH titration. And so how many milliliters? Well, X is the number of milliliters. We just solve for X. X will give us the number of mils required. It's going to be more than 20. Maybe 25. something like that. Why don't you solve it and figure it out? Okay, I'm going to stop here and then we'll take a break and then start the lab.